Question 1 asks for the circuit symbol for a triac and to label its terminals. Well, a triac is like two back-to-back diodes with a gate connection. So it's a 3-terminal device and it's labeled MT1 and MT2. The Zener diode, we want the circuit symbol for this. Now this is like a normal diode, so there's our cathode and our anode, but we've got this extra little kick here, and that little kick there tells us that it's a Zener diode. Three-phase PVC flexible cable supplying 400 volt three-phase motor has been replaced, and we've replaced it with a neutral screened flexible cable. What advantages have the neutral screen cable got? Well, it's got better mechanical protection, it provides increased safety when we handle it live, and it provides electrical shielding with that screening. Which type of protective device is the term tripping factor used? Well, tripping factor is the same as fusing factor is for fuses. Tripping factor is for circuit breakers that will trip rather than blow. Define the term tripping factor. Well, it's the ratio of the MCB minimum tripping current to the MCB current rating. So this minimum tripping current is going to be more than the actual current rating. So a current rating, say a 16 amp MCB, it might not trip until say 24 amps, and so we'll get a ratio of 1.5. Two identical 100 kVA transformers of the same impedance are used to supply separate installations. In the first installation, the transformer is 20 meters from the boundary. In the second installation, the transformer is located within the installation. So we've got some distance there of the first one, and the second one is much closer. State the main reason why the second electrical installation, so the close one, will have a larger prospective short circuit current than the other installation. Well, it's going to have a lower impedance because the cable run is shorter, and so for a lower impedance we're going to get a higher prospective fault current because that current is going to be V over this impedance. E is describe the prove, test, prove method. So you must go into the exam knowing this prove, test, prove comes up again and again. So we prove that our meter is okay because we test a known live source. We then test the thing that we want to make sure it's isolated or whatever we're doing. We carry out the test, and then we prove again that the test instrument is okay because we go back to that known live source and we ensure that the meter is working correctly. Doing a polarity test to find out if the supply to a three-phase main switchboard has been isolated. Between which terminals would you test to clearly establish that isolation has taken place? Well, you test between phase and earth, and they're saying any of those two, and I would say and phase and neutral. So to clearly establish it, you need both of those, but they're only asking for one. Three-phase TPS cable is to be installed as the mains to a three-phase electrical installation. State two reasons why the loads in the installation should be balanced as much as possible over the three phases. So we've got the three phases. If we have too much load on one phase and not enough on the other, it will be unbalanced. And if we balance it, we can have smaller cable size, so we can minimize the cable sizing. We can reduce the neutral current. If we have it perfectly balanced, then we'll get zero neutral current. We'll reduce the heat losses, and we'll prevent nuisance tripping on the heaviest loaded phase. So if you put all your load on one phase, that's going to be close to the rating, the maximum rating of that fuse, and we're going to get tripping of the MCB. We're going to get nuisance tripping. So we balance the three phases. Recommended maximum RCD rating of an RCD socket outlets in a kindergarten. So kindergarten, similar to that of a medical installation, 10 milliamps. It protects a Class 1 electrical appliance. The RCD is operated. What has the RCD detected? So it's detecting an earth leakage current. That's all its job is, to test that there's any leaking to earth of the current. Two methods to provide starting torque for a single phase motor. So the main one is the capacitor. So capacitor start motor provides that change in the phase and provides a starting torque. The two windings can have different impedances, so that would be like the split phase motor, or we can have a shading ring on the shading pole motor. The two main ones are the two different winding impedances and the capacitor. Easiest method of reversing the direction of rotation of three-phase motor controlled by a DOL. So to reverse the direction of a three-phase motor, we reverse any two phases. We've got a star delta in there, so the easiest method of reversing the star delta is reverse any two phases on the supply to the starter. Three methods by which a lamp can produce light. So current through a filament, current through a light emitting diode, or current through a gas. So that's our fluorescent, that's our normal filament lamp, and that's an LED. Following diagram represents three loads with resistance 78.5 connected to 400 volts. So we've got a balanced delta connection with our three phase. Calculate the current, or the phase current flowing. So the current down one of these phases. The current down that phase is going to be our line current, line voltage, divided by that resistance. So we've got 400 volts divided by 78.5. Over here gives us 5.1. So we'd have 5.1 amps flowing down each phase. Calculate the line current flowing. Now the line current is going to be √3 times this phase current. And they've done a weird example there. They've increased the voltage there by √3, which I don't agree with. All I would be doing would be √3 times IP. Exactly the same result as this, 8.83 amps, because IL is equal to IP times √3. The power dissipated, so there's our power formula, √3 IL VL power factor. So we've got √3, there's our IL from the previous question, our VL is 400. It's a resistive load, we've drawn resistors in there, and so the power factor is just 1. There's no inductiveness, no capacitance, so a power factor of 1 gives us just over 6 kilowatts, and that's in a delta connection. If we connected them in star, we know that the star power is 3 times less than the delta power. So we divide by 3 to get just over 2 kilowatts. Most appliances in New Zealand operate at 230 or 240. If we've got a heater that's 2 kilowatts operating at 230, what's the power going to be at 240? Well, we're going to get an increase in power. One way we can do this is to calculate the resistance. So the resistance is V squared over P, and that's a transposition of P equals V squared over R. So we'd swap these P and R. So we get V squared divided by the power, which is 2000 watts, gives 26.45 ohms is the resistance of that heater. Now that won't change when we put 240 volts on, but the power will. It will be 240 squared divided by that resistance, gives us 2177.6 watts. Alternatively, we can look at the ratio of the voltage and square that. So 240 divided by 230 squared times that original power will give us the same answer. Question 3, we've got a three-phase motor circuit. There's no other connections to the circuit. So we've got a switchboard, our starter, an isolator and a motor. We've got HRC fuses on a three-phase switchboard here. The lockable isolating switch and DOL starter are located adjacent to the motor. Describe how to isolate the motor and wire in to ensure that it's safe to disconnect. So what we're going to do first, we're going to remove the fuses at the switchboard, and then we're going to test for isolation on the supply side of the DOL. And we're going to use the prove test prove method to ensure that the motor is isolated. By locking off this isolator and replacing the empty fuse carriers at the switchboard and attaching a danger tag here. B. The motor has been isolated and disconnected. The isolator, describe the actions to be taken to ensure that the work area is safe to be left unattended. So we're going to make sure all the covers are secure, and we're going to replace that danger tag that we put on there with an out of service tag at the point of isolation. The motor has been cleaned and the bearings replaced. No electrical work was carried out. We've got one of these multi-function test instruments with the required functions, so that means we've got insulation resistance test on there. 2 instrument tests need to be carried out on the motor to ensure that it's safe to connect to the electrical supply. The first test is the protective earthing conductor. For the other test, so we're looking for insulation resistance now. So the name, insulation resistance, the function, we're going to go insulation resistance test function, 500 volts range. We're going to disconnect the links on the terminal block of the motor. At the unconnected end of the flexible cable, test between each phase. And at the unconnected end of the flexible cable, test between each phase and earth. And we're looking for 1 mega ohms or more. So we're making sure that none of the windings are connected together, making sure they're insulated from each other, and we're making sure that none of those windings are connected to earth. You're required to put the motor back in service. Describe the actions to safely reconnect. So we test for isolation again on the supply side of the DOL. We make sure, even though we've isolated it before, we make sure again that it's definitely still isolated. We use the prove test prove method to ensure that the motor is isolated. Question 4. Low voltage electrical installation as a switchboard. Got an MEN installation, switchboard and distribution board. Which switchboard would be connected electrically closest to the point of supply? We know that the MEN, one of its characteristics is that it is electrically closest to the point of supply. So that would be the MEN switchboard. 3 other features of the MEN switchboard that we don't have on another distribution board. So we've got the MEN link between the neutral and earth. It's connected to earth via the earth electrode. The MEN switchboard can supply another MEN switchboard, and the main neutral can be connected. 2 methods of connecting a low voltage MEN electrical installation to the mass of earth. How do we earth it? We use an earth rod, which is a main one, but we can use a buried electrode or the metallic reinforcing. Question 4. We've got an MEN switchboard. The MEN link between the main neutral bar and the earth bar is missing. State 3 factors that would occur if there was an earth fault in the installation when the MEN link was missing. So this is all about what are the dangers if we don't put that MEN link back in. So the fault current path would flow through the mass of earth to the start point of the distribution transformer. The impedance of the earth is generally much higher than the main neutral, so we're relying on that mass of earth and the moisture in the earth to get our current back. and the fault current may be limited to a value insufficient to operate the protective device. So we've got a high impedance for that fault current to try and flow through because it's trying to get through the earth, so the current is going to be quite low, and then it may not be enough to operate the protection device. So if the protection does not operate, there could be a shock hazard on metal framed appliances. So there could be a voltage there to give a shock to a person that goes and touches it, because there's been a fault and it hasn't cleared because there hasn't been enough current to blow or to operate the protective devices. Low voltage MEN domestic installation is required to have a main earthing lead. So where is it connected to what parts? So we've seen this again and again. It's connected to the earth bar and it's connected to the earth electrode. What do we need on the end of the main earthing lead? Well, we need either we need a tag warning against disconnection. Question 5, we've got a 3-phase 4-pole induction motor, 50 Hertz, 400 volts, 8.5 amps, 85% efficient, slip of 4%, so we know our rotor speed is going to be 4% less than our synchronous speed. Line current lags the voltage by a phase angle of 35 degrees. So they haven't given us the power factor there, but they've given us the angle. The rotor speed of the motor, we need to calculate that. So we can calculate the synchronous speed first. The synchronous speed is the speed of the stator magnetic field. It's going to be 60F over P. 60 times the frequency, so 60 times 50. Divided by 2. Now 2 is the pairs of poles. So this P is pairs of poles. We've given the amount of poles. We're going to see that 4 pole. So how many pairs? We've got 2 pairs. Gives us 1500 RPM. Now the rotor speed is going to be slightly less than that. So we can find the slip speed. The slip speed is going to be 4% of the, and that should be 1500 in there. That's an error in the answer there. So 1500 times 4% gives us 60 RPM. So the rotor speed is going to be 60 RPM less than the synchronous speed. So synchronous speed is 1500 there, minus our 60 gives us 1440 RPM. And that's the speed that the rotor is going at. We need to find the power factor of the motor. So the power factor is the cosine of the angle. We're given the angle of 35 degrees. Cosine of 35 is 0.819 lagging. It's an inductive load, so it's lagging. The output power of the motor. So the output power of the motor is the electrical power. And the power is √3 VL IL cos theta. So I always remember it. √3 IL VL power factor. √3 times our 400 times our line current, 8.5, which we get from the question. There's our line current of 8.5, and our power factor that we've just calculated will give us an input power of 4823. Now the output power is the mechanical power of the motor. And the mechanical power is going to be the input power times the efficiency. So we're told that it's only 85% efficient. So whatever we put in electrically, we'll get 0.85 of that out. And so 4823 times 0.85 gives us just over 4 kilowatts of output power. Now the output power is always going to be less than the input power of the motor. Question 6, we've got a test carried out on a 3-phase 400 volt electrical appliance after it's been repaired. We've got a protective earthing conductor test out of range. This doesn't sound good. And we've got an insulation resistance test between phase and earth of infinity, which is a very high resistance, which is what we want. We don't want any connection between the phase and the earth. or things tend to go bang. So what we've got there, we've got a faulty earthing conductor. We've got an open circuit on the protective earthing conductor. State 3 actions that need to be taken to ensure that it complies with 3760 and we can put it back into service. So we're going to repair the faulty protective earthing conductor. We're going to carry out another test to ensure that it's less than 1 ohm or less. And we're going to, once we put that back in, we're going to conduct an insulation resistance test to ensure the insulation resistance is 1 meg or more. Because this infinity might have been because this conductor was broken. So there might still be a fault there. So once you've fixed this earthing conductor, you've tested the earthing conductor is okay, you must retest the insulation resistance. Insulation resistance, we use 500 volts DC. Why do we use 500 volts? So it's to stress the insulation, to make sure there's no nicks or cuts or thinning of the insulation, to make sure that it's electrically safe. So we want to stress it above the peak of AC. Now the peak of AC is about 325 volts, which is that 230 divided by 0.707. We're going to stress the insulation at a voltage twice the RMS voltage of 250. So RMS is 250, 325 is peak. So as long as you say about stressing it and quote either of those, is the correct answer. Why is it DC? Well, I always thought it's DC, so it's a continuous voltage, so we're stressing it without just momentary peaks, as they say, of an AC waveform. We're keeping a constant voltage there, and if it passes that test at 500 volts DC, then we know it's going to be okay at 230 volts AC. There's also this thing of a capacitive or inductive reactance does not influence the test result. So if we put in an AC voltage in there, we could produce XL and XC that's going to mess about with the result. So if we put straightforward DC, we know that that's not going to take place. I think the easiest one to remember though is that it's a constant maximum voltage. The minimum insulation resistance, as we know, is 1 mega ohm, but it can be reduced to 10,000 ohms if there are MIMs. So we come across this lots of times. As soon as we see MIMs there, alarm bells, it's not the 1 mega ohm, it's the 10,000 ohms. So why do we allow a lower resistance? Well, it's because MIMS elements absorb moisture. And so they're still electrically safe, even though the resistance is well below 1 mega ohm. And as that heats up, that insulation resistance is going to increase because the moisture is going to disappear. Why is the polarity test carried out on the mains of a single phase low voltage electrical installation? So that's to make sure that we haven't got the phase and the neutral around the wrong way, that there's no transposition of phase and neutral. An earth fault loop impedance test at the main switchboard shows the results of 50 ohms. State one reason why such a high test result would be obtained. So we've obviously got problems there because that kind of resistance, we can have, if there's a fault, the current is going to be very, very small and the protective devices are not going to operate. So one of the main faults is that the main neutral is open circuited. And so this 50 ohms is the resistance through the earth. Or we could have a high resistance joint in the main neutral. Method of installing cables depends on the environment and in which the wires and cables are to be installed. TPS sheathed PVC cables are installed in electrical installation both indoors and outdoors. State two reasons why some TPS sheathed cables would be installed in PVC conduit. So if we're going to put TPS in corrosive environments or where they need mechanical protection or underground or in concrete, or if we want to provide environmental protection, then we need to install them in PVC conduit. So we can use it outside, but it must be protected. State 2 design requirements to be considered when PVC conduit is used outdoors. So impact protection. So it's no good having it very low down where it can be kicked or knocked. The effect of UV rays, so the sun is going to affect it. Use of expansion joints due to temperature, and the environmental conditions. So we need to make sure the environmental conditions are not too extreme for the PVC conduit. Extra low voltage cables are installed in the same conduit as low voltage PVC cables. State the reason why the extra low voltage cables are insulated to 230 volts. So although it's only an extra low voltage, we do need the cables insulated to 230 volts so that if there is a fault on the low voltage system, on the 230 volt system, it isn't transferred to the extra low voltage system. So we make sure that they're electrically insulated from each other by the insulation. And so the extra low voltage has to have better insulation than normal because it's going to be sitting next to 230 volt cables. Within insulation, cables are installed in open cable ladders and open cable trays. Some of these are going to carry large currents. Why do we need to fasten them down in horizontal cable trays? Well, if we get a very high current, a prospective short circuit current, so if there's a fault and we get high currents flowing, then the cables, because of the current producing magnetic effects, are going to start to repel or pull together, so they're going to move, and so we need to tie them down and securely fasten them. Telecommunication cables are installed in separate compartments to low voltage cables in the same cable tray. So why are we keeping them separate? So it's to make sure that any fault on the low voltage system, which is our 230 volt system, is not transferred to the telecommunication system. And it's also to make sure that the voltage is not induced into the telecommunication system. So if we have switching of that high voltage, we could induce voltage into the telecom system, and so we want to keep them apart. What provision is made where open cable tray passes through fire rated wall of a switch room? So we're going to seal it with a fire resistant sealant. Main effect on TPS cables that are installed through walls containing thermal insulation. So if they've got thermal insulation around them, they're not able to get rid of their heat, and so it's going to reduce the current carrying capacity of the cables. So it can't carry as much current through the thermal insulation as if it was open to air. Two factors that reduce the life of an incandescent lamp. So if we get too much voltage, it will decrease the life. If it's vibration, lots of vibration, that will mechanically reduce its life. Ventilation can affect it, and frequent switching, because when we switch on we get a higher inrush current, and if that's done lots of times, frequently, then it reduces the life of the lamp. The main color of high pressure sodium is yellow, and the main color of high pressure mercury is white. Fluorescent lighting is installed mainly in commercial or industrial installations. State the two main functions of the ballast. So the ballast has got two jobs. It limits the current through the electrode and the tube, so when the lamp is running, it limits the current that flows through the tube, but it also has the job of starting the lamp. So it produces the high voltage when the starter opens to start the tube glowing. So we looked at that in the previous question, where we get the current flow through the tube, or through the ends of the tube, that warms the ends of the tubes up. The glow starter opens, and the field in that ballast collapses and produces the high voltage to strike the lamp. Power factor correction is connected across the supply. So why do we need power factor correction? It's because of that ballast. That ballast is a coil, and that ballast is highly inductive. So it's highly efficient if we just have all inductive loads. And so we put the capacitor in there to try to cancel out some of that inductiveness. And the EMI suppressor connector capacitor is connected across the glow starter. If it short circuits, what's going to happen to the operation of the fitting? Or if that is a short circuit, then the glow starter opening and closing isn't going to have any effect on the circuit, and so we're not going to get that collapsing field. So the lamp's not going to start. The lamp will glow at the ends because we'll still get that current through the ends of the lamp, and so they'll glow, but the lamp will not strike. Any one of those will give you the 1 mark. Machine shop has got rotating machinery, it's got incandescent, so our normal filament lamps, and fluorescent lamps. So why we got the two together? It's because if we just had fluorescent lighting, we can get that stroboscopic effect. So it can appear that the machinery is stationary. And so we need to put some of this incandescent filament lamps in so that we get a constant light. So the answer they give, to reduce the stroboscopic effect of the fluorescent lighting. 4 requirements for good lighting. So sufficient light for the application, minimum glare, a uniform light, and the correct color. 2 precautions when handling and installing halogen lamps. So halogen lamps we shouldn't touch with our hands, with our fingers. They should be installed in the horizontal position only, and we shouldn't cause too much vibration to them. We should handle them very carefully without touching them with our fingers. 3-phase RCD is protecting a sub-circuit supplying 3-phase 5-pin socket outlet. Describe the internal operation of the 3-phase RCD when there's a active phase to earth fault in an appliance that is plugged into the 5-pin socket outlet. So we've got an earth fault. So if there wasn't an earth fault, then the 3-phase currents would balance and the neutral current would be equal to that sum of the 3 phases. And so like in a single phase where the phase and neutral of the RCD cancel out, in a 3-phase the sum of the currents cancels out with the neutral current. But now we've got a fault in there, we've introduced a fault, and so there's going to be an imbalance between the neutral current and the sum of the phase current. And so we're going to get a magnetic field induced into the iron core, and that's going to induce a voltage into the sensing coil, and once the sensing coil sees a voltage, the tripping coil is energized, opening the RCD contacts. An RCD test has been carried out on a PRCD, so portable residual current device. Device passed the trip test. What additional checks must we carry out? Well, we need to make sure that it's voltage dependent, that it automatically or won't automatically reset once the supply is put back on. So if we lose the supply, the PRCD should trip out, supply comes back on, it should not come back on. It needs to be manually reset. An existing 230-volt MEN domestic installation has no RCD protection on the switchboard, and we're putting a new socket outlet in a zone 2 of a bathroom, and we've got 3 other socket outlets on there. So we want to give protection, RCD protection, to the new socket outlet in the bathroom. So how are we going to do that? We could install an RCD at the switchboard of the origin of the final circuit, so we could put the RCD in the switchboard, or we can install a socket outlet RCD on the bathroom socket outlet, the one that we're going to put in, or we can put a socket outlet RCD on a socket outlet upstream from the first new socket outlet, and that will protect all of those downstream. So either at the switchboard, at the bathroom socket outlet, or upstream from that bathroom socket outlet. RCBO, so this is going to give us earth protection like a normal RCD, but we've also got overcurrent protection and short circuit protection. So the two other type faults it would protect against would be overcurrent and short circuit. The phase neutral on the supply side of a single phase RCD has been transposed. Would the RCD operate if it detected an earth leakage fault on the circuit it protects? So yes, it would, because the RCD doesn't care if the phase or neutral is transposed. It's just looking for an imbalanced. So a transposed phase and neutral, as long as there's no imbalance, then the RCD is not going to trip.